So this next chapter is on reacting mixtures and combustion. And it's really, combustion is a particular type of reaction occurring with mixtures. So it's not a very general chapter. We're really focused on combustion. But there's a lot to do in combustion. But when you have a general reaction equation, how do you write a general reaction equation? Thinking back to your chemistry. Products, reactants, and a little symbol in between saying, hey, I'm starting with some reactants, and I have a reaction, and the result is some products. So the idea of putting reactants on one side, the left-hand side of an equation, and the products on the right-hand side, and we're going to assume this is the notation saying it's going to complete, it's going to completion. The next chapter, there's a different chemistry notation, and it's like it goes into a balance. And if I change pressure or temperature, it may push it more toward the right-hand side, or if I change pressure temperature, it may push it more toward the left-hand side, depending on what type of reaction it is. But the equilibrium mixture will have some of what's on both sides of the equation. That's not what we got here. It's just what starts in reactions goes to products. All right. So combustion. What's the key for combustion? You need a fuel. And so we have basically a fuel plus an oxidizer. Now, oxidizer is a very general term, but guess what our oxidizer is? Oxygen. And we're not going to get innovative and start having different oxidizers. We're just going to really have a very basic chemistry. Because what we can do now is we can take a lot of our tools of thermodynamics and really rigorously apply it to understand, let's say, the heat of reactions, the temperature changes of the products from the reactants when we undergo. So we can do a thermodynamic analysis of the combustion. So what are some common fuels? What are some of our hydrocarbon fuels? Just straight off the top of your head, thank you, methane would be number one. So methane is CH4. Hopefully you could say, oh, CH4, that's methane. That's kind of nice to know. Somebody says, I don't know that. Memorize it. All right, CH4 is methane. Where do you maybe have purchased methane to burn it or combust it in your life so far? Or maybe your parents' household? You would basically, some grills are hooked up to methane, but a lot of them are propane. How about for heating inside a home? Furnaces burning natural gas? Natural gas is primarily methane. It's overwhelmingly methane. It's like 90-some percent, 99% methane. All right, other than methane, another one, hydrocarbon that we burn a lot of. Octane, which is your basic. If somebody said, I know gasoline's a mixture of a lot of things, but give me one element that I could model gasoline as, it would be octane. That would be the C8H18. So how many people have purchased gasoline? Sure, we all have. Or if you haven't, you've been driving around and somebody else has been paying for it, right? And then another one that I heard somebody else say, propane. So how many people have propane grills? You can buy little tanks and turret them in and get the propane. Or CPS tries to have natural gas to a lot of homes around here, but they don't go to all the homes. And so if you have maybe a propane tank that you burn in the winter for heating of your home, maybe if you're more rural instead of in the inner city, how many people know if they have propane heating in their home? Nobody has a propane tank at their home? Only one? There's usually a few that do, okay? Yeah. So these are at least 3 hydrocarbon fuels. There's other ones. Acetylene. How many people are welders? And yeah, acetylene is a hydrocarbon fuel. Now, where do our products go? Notice what's the pattern in each of the hydrocarbon fuels that we've listed 3 of them there. There's carbon and there's hydrogen. And I remember when I was a student, this always baffled me. It's like, why doesn't the carbon like to go over here? Or why doesn't the carbon like to go over here? The carbon always likes to go to CO2. Not CO, not CO3, not C2O8, whatever else. It's not. It's just CO2. It goes back to your study of chemistry, the happiness at the lowest energy state, and it's just content to be there. All right, when you burn it. And then where does the hydrogen go? You know, why doesn't it go to HO? Why doesn't it go to H2O2? Why doesn't, you know, these are questions that other people can answer better than me. It just likes to go to water. And if you're going to burn it and the products are hot, it's going out as water vapor. Water vapor. So we get the oxygen from where? That's a very simple question. We get it a lot from air. But if you have big bucks, you can actually purchase oxygen in a tank that's pretty pure. And so you can get pure oxygen. And maybe you are NASA and you want to get a rocket and you want to really throw a lot of fuel products out the exhaust of a nozzle. And maybe you do have oxygen on there. Maybe you burn it with hydrogen, pure hydrogen. Maybe that's very expensive, but you know, you can do that. Now you get air. Oxygen comes from the air. Well, what goes along for the ride? Nitrogen. Now, a very simple model is we're going to say that the mole fraction of oxygen in air is 21%, and the mole fraction of nitrogen in the air is the remainder, 79%. Does that add up to 100? We know that there's some carbon dioxide. We know there's some argon. We know that there's other constituents in air. But this is a very simple model. So I can write an equation and say if I brought in 1 kilomole of air, how many kilomoles of oxygen would I bring in, and how many kilomoles of nitrogen would I bring in if I brought in this air with that makeup? 0.21 kilomoles of oxygen and 0.79 kilomoles of air. Somebody asked the question, how many kilomoles of air would I need to bring in precisely 1 kilomole of oxygen if I was getting it from air? And if I brought in precisely 1 kilomole of the oxygen, how many kilomoles of the nitrogen would I bring in? I want everybody to do this. I'm going to stop, pause, walk around, okay? I'll get this question asked different ways a lot of times. So why do we have this 3.76? Why do we have this 4.76? Where does it come from? Well, it comes from right here. So you took this equation and what did you do? You multiplied by 1 over 0.21. And 1 over 0.21 turns out to be 4.76 with some change, but let's round it off, right? Because how accurate is this number? Not very. 2 significant digits. So we're pushing it to get 3 significant digits on the 4.76. And then right over here, this is 3.76. So you'll see sometimes either it's 4.76 or 3.76. It depends what you're asking. To bring in 1 kilomole of oxygen, I need to bring in 4.76 kilomoles of air. It'll also come with it 3.76 kilomoles of nitrogen for the ride. That's what I like to say. It goes for the ride. Okay? All right. Stoichiometry. So we're going to balance reaction equations. I encourage you to take a look at some general websites. This is easy to read. It's a very easy website. And they talk about these stoichiometric coefficients. What is the stoichiometric coefficient? It just tells you how many entities, like how many kilomoles, go in their equation, right? So instead of writing 1 kilomole of air, you could just say 1 air. And then you know, oh, that's 1 kilomole. All right. So down here, this is a reaction equation. That's 2 is a stoichiometric coefficient. That 2 is 1. That's another one, and the 1 is a 1 stoichiometric coefficient. Now, you've all had a chemistry class probably in high school. You all had a chemistry class at the university level. It's required in our program. So you're familiar with stoichiometric coefficients. But every semester, I'll get asked this question. It's like, you're breaking the most important rule the chemistry professor taught us. And that is, you're putting a stoichiometric coefficient that's not a whole number. Or it's not a fraction. Well, guess what? They prefer, it's often preferred to have whole numbers or even nice clean fractions. But is it really required? Nope. And so I'm going to use that 4.76 or that 3.76 often. It's a decent stoichiometric coefficient, okay? Now, if somebody says, well, you must use a fraction. Well, great. Then I'm going to put 21 over 79. Or 79 over 21. You could put that, but don't do it. Let's put in the 3.76 for the number of moles of, or stoichiometric coefficient on the nitrogen. Let's solve this problem. We have propane, it's C3H8, and it combusts with air. That's key, telling you where you get the oxygen from. It's coming from air. Obtain a balanced reaction equation for complete combustion with theoretical amount of air. So the complete combustion is pretty easy. All of it's going to get broken up. There's not going to be any propane left in the products. It's all going to go away. It's all going to be broken up. So what we do is we write down the fuel, C3H8. We're getting oxygen from air, O2 plus 3.76 N2. That's a good way of representing the air. If I want to, I can sometimes put a 1 in there, but I don't have to. And I leave a space out here with the unknown coefficient, and that's going to basically get a stoichiometric coefficient in that equation. That's everything of the reactants. Now we go to the products. Where did we say the carbon wants to go? CO2. So we put CO2 over there, but we don't know how much. We're going to have to balance this equation. And then the hydrogen wants to go to H2O. We don't know how much, so we leave a space for the stoichiometric coefficient. And if it's theoretical air, how much extra air did we have? Nothing. We had only the perfect amount of air. If you have the perfect amount of air, is there any unused oxygen? Nope. If you had excess air, there would be excess oxygen. But it's no excess air, it's theoretical air. Sometimes we'll say it's 100% theoretical air to just emphasize it's the perfect amount. So there's no excess oxygen, but is there any nitrogen in the products? Yes. And you could put the 3.76, it's like it just goes with it, and then I'll have a little coefficient right there. So there it is. Now, somebody says, why don't we just have a coefficient in front of the fuel? You can, but this is like rule number 1. Put a stoichiometric coefficient of 1 in front of your fuel. And once you do it, don't change it. Don't go back and say, oh, I think I'm halfway through balancing this equation. I think I'll now change that coefficient. It'll make my life easier. No, it won't. Leave a 1 there. Now the next thing you do is you say, I need to balance this equation. Let's do the carbon first. You don't have to, but let's do the carbon first. If I look, how many carbons do I have on the left-hand side? I have 3 carbon kilomoles, or 3 carbon moles, or whatever you want to count. Now what do I have? How many carbon do I need on the right-hand side? If I have 3 on the left, to be balanced, I must have 3 on the right. Where's the only place that carbon is on the right-hand side? In the CO2. And there's a subscript 1 on this carbon. When we have a subscript 1, we just don't write it. So how many CO2s do I have in the products? You're good. Now, after you balance the carbon, balance the hydrogen. Come over here, and on the reactant side, how many hydrogens do I have? 8. Don't go faster than your neighbors. Your neighbors everybody's got to keep up. So I look at this. I must have 8 over here. 8 equals 8 for the hydrogen balance. Where's the only place that I see the hydrogen? Is water HO2 or H2O? And there's a big difference between these two, isn't it? So what's the coefficient in front of the H2O? You are good. It's 4. Now we do the oxygen. We did the carbon, we did the hydrogen, now do the oxygen. If you do the oxygen, work backwards. Start with everything on the right. How many oxygen do I have on the right? Go slow. This is my warning right here. S-L-O-W. Do the oxygen very slowly. So just how many oxygen with the CO2? 6. How many of the oxygen with the H2O? Right there is tricky. Some people write 3 plus 4. Did they make an error? Yeah, they made an error. So we add those together. 10. True? Now I push back this way and I say, I can now determine the coefficient in front of the air. That's right. It's 5. Sometimes I'll even write it 10 halves. I don't know why I'll do that, but it's 10 halves, okay? But it's actually 5 in this case. Now the last thing we need to balance, we did the carbon, we did the hydrogen, we did the oxygen, we need to do the nitrogen. This is pretty easy. That's why I left the 3.76 over here. Make sense? Good. So this is our balanced reaction equation for combustion of propane using theoretical air. Let's review what we did. So if you have to balance equation for some combustion of a fuel, put the reactant, that's the fuel, and the air on the left-hand side, and the products, and the products are going to go to CO2, water, and then leave the nitrogen over on the right-hand side. So the fuel plus the air is on the left. Pick 1 for the stoichiometric coefficient in front of the fuel that's on the left-hand side and leave it alone. Don't change it. Here, no matter what the temptation, do not change. Put the air like that. The 1 times the oxygen plus 3.76 times the nitrogen. You don't have to, but it's a lot easier. Leave a place for a stoichiometric coefficient in front of the combination of the air, so that if you bring it up, the nitrogen goes up with it, even in that parentheses. Leave an unknown stoichiometric coefficient in front of the carbon dioxide, in front of the water, and in front of either the 3.76 nitrogen or just the whole thing. Then, once you know where you need to find those stoichiometric coefficients, do a carbon balance to get the first one on the CO2. Then, hydrogen balance to find the coefficient in front of the water. Then, the oxygen balance working backwards, BACK, to do it in front of the air. And the very last, the nitrogen. Pretty easy? So this was our balanced reaction equation for 100% theoretical air burning the propane. Did I write it down correctly? Looks good? Now let's do this. They say no. Now I need a new balanced reaction equation for complete combustion of the propane with 20% excess air. Well, first of all, what's 20% excess air? So we have 120% theoretical, 120, I've got to write this right, 120% theoretical. Air is exactly the same as 20% excess air. So if you were given this problem, the first thing is do it for 100% theoretical air. Get that correct. Now, copy it down and modify it. Do I want to change the 1 in front of my fuel? Leave it alone. Leave it alone. But what we're going to do is we're going to put a new coefficient in front of the 5 and in front of the O2 plus 3.76 N2. And then what we're going to have is we're going to take, and you can rebalance the carbon dioxide, you can rebalance the water vapor. Do you think you'll have any unused oxygen if you have excess air? We sure do. And we're still going to have the nitrogen. I didn't leave enough room, 3.76. Okay. If you do the balance on, first of all, what does it mean to be excess air? What do I put right here? 1.2. That's exactly right. 1.2. Now, I would leave it as 1.2. Somebody already said, hey, that's 6. You can replace it by 6 if you like, but I would leave it as 1.2. To me, it's real clear. Oh, it's 120% of what is theoretical. Okay. Now, let's go ahead and do the carbon balance. Let's only have somebody in the first 2 rows. What's the coefficient in front of the carbon balance? 3. Did it change? Nope. The next 2 rows, rows 3 and 4. What's the coefficient in front of the water? It didn't change either, did it? All right, so now row 5 and 6. What's the coefficient in front of, let's do the nitrogen. Let's do the nitrogen, rows 5 and 6. It's the 1.2 times the 5. It's 6. All right? Now, everybody in the last 3 rows. All right? Let's do the oxygen. And I'm going to pause, actually. I want everybody to do the oxygen. I'm going to pause, walk around. You do the oxygen. Show me. This can be tricky. All right, so a lot of us have it correct. It's a 1 here. But what's the common error? They'll put a 2 there. If they put a 2 there, what did they forget? They forgot that 2 down there. That's what they forgot. Right? And so it's tricky. We're balancing the O's, not the O2s. We're balancing the O's. And so if the answer is a 1 right there. Agree? Very good. Now that we have it for excess air, get a new equation, this time the same fuel, propane, oxygen from air. We want a balanced reaction equation. If you have 90% of the propane is consumed in the reaction with the 100% theoretical error. So what happens to the 10% that's not consumed? It goes out in the products as propane. So I would always get to this benchmark, 100% theoretical error. Redo it again, get there. Now modify. So, do I modify the C3H8? Do I put maybe 0.9 here? No, that's right. So leave it as a 1. Now, do I modify the 5 in front of the O2 plus 3.76 N2? It's still only the perfect amount of air if there would have been complete combustion. But what we have is we have some unknown CO2, some unknown H2O, some unknown C3H8. Isn't there going to be some leftover fuel? Will there be some leftover oxygen? And will there be, there's nitrogen going for the ride. What I want to do is I want to pause, walk around. I want you to help fill these in. So let's wrap this up real fast. Let's do this. We have 0.1 on the propane that's not used. So I know that some people still wanted to change that. You leave a 1 right there. Okay.
I'm sorry, can you explain that?
Because 10% is not used. But so 10% goes out as in the products. And remember, it's the products. Yeah. Okay. So now we rebalance the carbon, and most people were able to get 2.7. You rebalance the carbon. That's probably not the hard part. You rebalance the hydrogen. And all of those you have to remember, hey, there's some carbon right here. There's some hydrogen right there. The hardest is the oxygen. Let me do it slowly on the oxygen. We have 5 times 2 on the oxygen on the left-hand side. True or false? Okay. We have 2.7 times 1 plus 3, times 2. 3.6 times 1 plus unknown x times 2 or not? It's times 2. That unknown x is times 2. So if we take this equation and solve for x, if you put a 1 there, what did you probably forget? True? How many people agree that x needs to be a half? All right, so there you go. 1/2. And then what do we have down here for this coefficient on the nitrogen? 5. You're all excellent. I have to stop and pass back the exams.